Okay, we can get started. Thank you all for coming to the CISE Hariri Distinguished Speaker series. Today's talk is by Professor Asu Ozdaglar. She is the Mathworks Professor of Electrical Engineering and Computer Science at MIT. She is also the Department Head of EECS at MIT. She also holds the position of Deputy Dean of Academics at the College of Computing at MIT. She's an expert on machine learning, control, networks, and economics. And she has received numerous awards throughout her career, including industry awards, teaching awards. She's a fellow of the IEEE. She's a fellow of the International Federation of Automated Control. And thank you so much for being here with us today. Thank you all for coming. And without further ado, thanks.
Thank you. Thanks very much. It's great to be here in such a gorgeous building. I kept taking pictures so that I can go and make people at Lids jealous. I thought I could talk about today, a passion in my research group, which is really multi-agent optimization and control. Essentially, over the past couple of years, we're very interested in combining sort of ideas from game theory and RL, reinforcement learning, and see what we could do in dynamic environments in terms of learning, adaptive agents, learning together in a common environment. And I call it independent learning dynamics. That's coming from very much game theoretic ideas. I will assume that these are autonomous agents. We're not designing algorithms, but we're really designing learning dynamics, independent, uncoordinated learning dynamics with these agents, and seeing how these could converge. Those kinds of dynamics are very challenging in game settings, even in static, repeated play of static games. So we're going to try to sort of extend that to the stochastic dynamic settings. And I'm going to talk about a bunch of papers. I try to highlight a few ideas, key ideas from several papers. And I have a bunch of collaborators listed there. Probably I'm not even listing all of them, but many of the papers are joint with Kai-Ching Zhang, who was my postdoc. Force of nature. I learned a lot from him in reinforcement learning. He's now a faculty member at Maryland. Chen Wu Park is a student at MIT. Mohammed was a postdoc with me, now a faculty member at Bill Kent. Francesca was a postdoc with me, faculty member at Cornell. And also we're going to talk about asymptotic behavior, convergence, but also lately it's basically we view essentially a single autonomous agent making decisions or learning to maximize a reward using sequential actions in an unknown dynamic environment. And this has really emerged as a backbone of many AI kind of problems. So of course, self-driving car is a very sort of well-known example. You have a single agent sort of taking actions. Think about this as driving maneuvers. That gives some reward, maybe travel time, maybe safety. It has a state underlying decisions so that the agent takes decisions, the state changes, vehicle's position, speed, surrounding environment, and this sort of moves on. So that sort of captures the dynamics in the environment. And this is sort of what we mean by single agent learning in an unknown dynamic environment, and it has a very rich history in optimization control, now AI. But there's also recent recognition that agents do not act in a vacuum. There are many of them. Your actions impact others. So these learning paradigms need to be embedded in these multi-agent settings. And I mentioned autonomous vehicle control as an example, but there's many other examples, and I think you can add to this list. But many people are very interested in sort of these games, chess, Go. Of course, they're not stochastic, they don't have the Markov structure. Those are more extensive form games, but there's a lot of the RL ideas there. Think about, multiple robots maybe acting together and affecting each other. This could be control of UAVs. There's a lot of work in automated warehouses, production facilities. And I guess the application I'm most interested in, or where I want to move this, is sort of the human-machine interaction. Sort of that's driving many of this interest in adaptive agents, different learning rules, how do they sort of combine? And if you look at how to think about designing these kinds of dynamics or learning rules, really, these are multi-agent interactions, so you need to think about decision and learning in such environments. And that brings us to game theory. And of course, Nash equilibrium, I don't need to introduce that to this group, but it's a remarkably powerful tool for understanding multi-agent interactions. I like the example of traffic games in thinking about, game theoretic scenarios. Well, first, it's very practical. It's our life. All of us basically go through that every morning, probably. If you have a kid, you would know what I'm talking about better if you're commuting for school. Here we have agents who are commuters going from home to school or work. Actions are the many routes they take. Reward is, they want to get to their work as quickly as possible. And Nash equilibrium there is really a configuration, a stable configuration whereby no other choice of routes can, save you time, right? So that's sort of the idea. It's a stability kind of notion, equilibrium notion, but most economists and computer scientists, control theorists, have come to think about it as not so much arising from, introspection or calculation, but rather from some form of non-equilibrium adaptive process of learning, so dynamics. And, if you think about my traffic example, there, we don't think about each agent taking their route choices by contemplating the best response, like the rational play of all other agents, computing their best responses. Rather, play basically proceeds by trial and error learning and, converges to some stable configuration at the end. So that brings us to multi-agent learning and static and dynamic games. And this is a very, of course, rich history in game theory, probably as old as game theory itself. One of the best studied models, which I'm going to use throughout the talk, is what is known as fictitious play. And that's a very simple model, but basically says you have myopic agents. We estimate Rabia's strategy. I look at Rabia's actions throughout, and I assume that her empirical play is a good approximation for what strategy she's using. Of course, that is changing, right? But the assumption is that that's sort of some stationary strategy that players are using. And then every player, against that estimate, uses a best response time type action in the static games using their stage payoff at each round in the game. And there's a large literature in economics that Robinson showed that this converges in zero-sum games. And then there was a lot of, I didn't cite much of the literature here, there was a lot of interest in showing what kinds of games, there was excitement, right? Maybe we found a way to explain why Nash equilibrium arises, like if you can show that fictitious play converges in all kinds of games. So that was the research program for a while, until Shapley found the counterexample, which showed that fictitious play doesn't converge, there's cycles and so on. So then that moved, I think, the community to what classes of games are nice in terms of its learning dynamic behavior. And beyond zero-sum games, Monder and Shapley is the first paper that shows that for potential games, that's another benchmarking game sort of space of games, also admit this nice behavior in learning dynamics, fictitious play learning dynamics. And then there's a lot of other extensions in thinking about what kind of games have this kind of nice behavior. Great. So this is a lot of literature that one learns in a game theory class. But if you look at what happens in dynamic environments, which is what I was motivating, there's very limited progress. And the key challenge is, as I mentioned in fictitious play, you're estimating, these other agents' play. When you have adaptive agents doing the same thing in a common environment, what you end up having is each agent is operating in a non-stationary environment. Everybody is trying to adapt. And if you look at RL settings where, you don't have a model of the environment, it's model-free, transition probabilities are not known, payoff functions are not known, it becomes very challenging to put these things together. And I think that was the reason where we haven't seen much progress. I actually worked on this problem about 10 years ago without much progress. So I was very happy last few years when we said, these things seem to be working. So that's why I think it has been driving my interest in this area. It's mathematically very interesting set of problems. Okay, so let me say a few words about classic results in stochastic games. I view them mostly computational in nature and for zero sum. So Shapley has a paper in 1953 which defined for the first time stochastic games. And this is basically get this matrix game that I just told you about, normal form games, extended to dynamic environments, or MDPs, which was very Markov decision processes, which was very active, I guess, at the moment. Extend this to competitive situations. And Shapley's paper introduced the notion of a stochastic game as a framework to study these kinds of environments, but also showed a minimax value iteration type algorithm essentially operates, writes synchronously over all possible states. It's an algorithm, and then can compute, if you read the proof, it's a page. It has a nice contracting property in discounted games and nicely converges. Nice. So that was 1953, and in game theory literature. Then you look at Littman from 1994, another key paper in this area, in AI literature, which actually looked at, if I don't have the model, what do I do? If I don't have transition probabilities. And Littman basically introduced a Q-learning type sort of asynchronous updates over states in stochastic games. And then this sort of convergence in zero sum was proven by Littman, Sepeshvari, who Bowling has some non-zero sum versions of it, which is, again, basically involves things like at each iteration, I compute an equilibrium fixed point at each iteration. So it's really very computationally challenging and also really algorithmic. Again, not really this learning dynamics flavor that I was talking about. Perfect. So that's classical. There's some recent, explosion of activities, both in control, if you look at, machine learning type conferences. And I tried to sort of, organize it in two different set of settings. One is what I call more like a centralized learning setting, where you do have a centralized controller that jointly optimizes. You have multiple agents, but you have a centralized controller, a joint simulator that can actually, compute things jointly. And then the other one, which is more challenging, is this decentralized, or what I will define as independent learning. Agents optimize their own payoff given their own local information. Okay, so this is the setting where, you could call it distributed because agents have local information. You can call it, these are agents that are self-interested, so they have no interest in following an algorithm that you design for them. Or maybe the scenario or the setting is so complicated that, you don't want to design very, brittle rules for agents to follow because it may be impractical to do this. And when you go into these more independent or decentralized learning settings, there are some fundamental challenges because of the non-stationarity I outlined, even when you have oracle access to the game. So if you have, for instance, given opponent strategy, there's a black box that gives you the exact Q functions, naive rules can actually cycle and not converge. So that's sort of, Condon is a nice paper to read in that setting. So this is the background or context against all of these things. Two papers got my attention in this area. So one is by Daskalakis and co-authors, where they looked at a zero-sum game, policy gradient method, and then they coordinated the agents' learning rates. They said, Yanis, you go fast, I will go a little slow, and then they showed some convergence. Leslie is an economist around a similar time studied the continuous time best response dynamics for these games. Assumed there's some common continuation payoff that all agents can access, and then using that as a coordination feature sort of has some dynamics that showed convergence. But both of these are, I think, nice ideas, but because you're getting convergence, but it requires coordination, right? You either need to coordinate agents, you want them to access a global information. There's also, in the potential other extreme, there's some policy gradient methods. Essentially, I view them as algorithmic approaches for equilibrium computation. Okay, so a long introduction. I guess the question that I've been always interested in is, can we identify reasonable and independent learning dynamics that converge to Nash equilibrium for stochastic games? Reasonable, by that I mean basically agents are acting in their own individual interest. So they have a payoff function, they have some observation. Given that, they do best response against that. So they don't follow a rule, they just do whatever is best for themselves. Independent, meaning no coordination among agents. And then the second question that sort of motivated our work was, can we provide finite sample guarantees for best response type dynamics? And then that came with the recognition that even for matrix games, these kinds of sample complexity guarantees are not commonly known. Okay, so that's basically what this talk is about. In a couple of recent papers, we developed some simple learning rules based on this best response fictitious play type dynamics that are decentralized and independent. So our first paper on this is for zero-sum stochastic game. Complete information. I will define all of that in a second. This is with Mohammed and Francesca. Then with Leslie and Tamer, we basically said, what if we are in settings where you don't have access to a lot of information? So that will be the minimal information version. And then I will talk a little bit about finite time analysis for these games. And finally, this was, even though I was very happy, we have something for dynamic games, it's for zero-sum, two-player games. So I think the next thing to think about is, how do we go beyond two players? What kind of structures are, allow us tractability in terms of moving forward with more general sets of games. And I will basically define a multiplayer version of networked Markov games, which is our recent work in that area. Okay, so the main ideas, what allowed us to finally get some results in the setting, is what I call the two-time scale learning. So it's very much motivated by the two papers, Costis's paper and David's paper, where they were doing two-time scale learning, but between agents. They were slowing something down. So here what we're going to do is we'll do that at the individual agent level. So each agent will be simultaneously estimating the opponent's action, as in game theory, and his own continuation payoff, as in dynamic programming. And we're going to basically do this in a two-time scale manner that, one of them is done at a faster pace and one of them will be at a slower pace. So that's sort of one of the key ideas. And then for finite time analysis, I will show you some tricks. We use some smoothing techniques that allowed us to get some convergence rate there. Okay, so that's sort of the outline of the talk. I will go maybe a little bit into the details, and feel free to stop me at any time. I have a tendency to talk a lot, so just if you have any questions, please stop me. Perfect. So what is a stochastic game? For those who have seen MDPs, start thinking about the Markov decision process. So we have a state space S. I'm going to look at finite state space. AI is so we have n players. AI is the finitely many actions that player I can take at any state. And then the player can actually randomize over these. So delta of AI denotes probability distributions over the set AI. Because we have multiple players, we're going to be interested in their joint action profile. What I played, what Yanis plays, what Rabia plays, A1, A2, A3. Okay? And then Ri is the stage payoff of a player at state S. Unlike single agent MDPs, this depends on not only my action AI, but all the actions of the other players. So that's one difference from single agent MDPs. The second is that the governing transition probabilities, P of S tilde S, does not just depend on my action, but depends on the whole action profile. So everybody's action essentially affect how this underlying Markov chain moves from state to state. And we're going to look at discounted MDPs. Perfect. And then I will focus on stationary Markov strategies. So we're going to look at a mixed strategy per state, which I will denote by pi I, right? For each S, I will have a probability distribution which determines the mixed strategy of player I, and pi is the strategy profiles. And then the payoff function, expected payoff or value function of player I, is nothing but a discounted sum of the stage payoffs, right? And then we start from some initial state S. Sk is just the stochastic process that determines the state transitions. And Ak here is drawn from this mixed strategy pi. Yeah, that's for the initial state S. And then if you take the expectation over the initial state distribution, you get your payoff for a given strategy profile. This is pretty classic. And the Nash equilibrium basically is pi star, such that when you fix other players, changing your strategy does not improve your payoff. So this is the equilibrium value function for all players. Okay, Nash equilibrium definition, I hope, is clear. Okay, so how do we go about writing down dynamics for this? We use basically dynamic programming or multi-agent extension of that, which is sort of a Bellman equation characterization of optimal value functions. And essentially what it does is it characterizes the value function as using also called one-stage deviation principle. If you deviate in one stage and then, follow your strategy from that point onward, you cannot, improve your payoff by doing that. So essentially, this is the multi-agent extension of the Bellman characterization. So the optimal value at state S can be obtained by maximizing over the current state action and following pi star from that point onward. Okay, so this is the usual Bellman characterization. As you can see, it involves a maximization and an expectation. And we generally, instead of doing that, we do something different. We use something, not the value function, but we use something called Q function, which is essentially this expression, pink expression here, right, inside the maximization and expectation. And if I do it that way, then V is nothing but maximization expectation of Qi. But basically working with Qi brings a beautiful mathematical convenience to me, because instead of having the expectation inside, what I did is basically having the expectation outside. So I can actually estimate these things better using simulations. Okay, so this is very classic, defining the Q function. But once I have that, so now what I will do is basically to define a learning dynamics for this setting, I will combine what Brown and Robinson defined using fictitious play with some value function or Q function iteration. I gave reference to Dimitri here, but I'm sure there's other references as well, but I've learned it from there at least. So we combine that. So what do? Players form beliefs on opponent strategies using empirical frequencies. Players also form belief on equilibrium value function or Q function. And then you choose a best response in this auxiliary game, given your belief, which is basically maximizing everything with respect to your Q function estimate. So the difficulty here is that, everything is moving in these kinds of dynamics. You're optimizing with respect to your estimated Q function at each point, but that Q function moves at every state. So essentially, unlike repeated play of stage games, which is already challenging to analyze, there at each stage, you take as your payoff the matrix game itself. Here, the auxiliary game that you form keep changing as your estimates of the Q function changes. Yeah. Yeah, so I'll go through, more and more refined versions. For now, everything. I can see your mixed strategy. Exactly. So that's the simplest. I just want to show you how we get convergence there, and then slowly, relax those requirements. So for now, I will see all of your mixed strategies. I know my own payoff function. So what kind of dynamics I can define with that? And here is the dynamics. And hopefully this doesn't look like too much of notation given what I've been talking about. Basically, at each iteration, I have a belief on my opponent's strategy, which is pi minus I. That's my belief. And on my own Q function, which is QKI. And what I do is, what player I does is, it selects the best response given that QK, right? This one. And then, you get your best response. Everybody does this. Everybody computes a best response. And then I'm going to update my belief on your strategy. I see your response, AKJ, and I just do it in some, convex combination between my current belief and the response that I see in this period, AKJ. So that's how I update my belief on your strategy, and then I update my belief on my Q function through a, very standard. You basically say, okay, this is my belief on you. I have my VKS, which is the realized payoff right now. I look at the realized payoff. This is my previous estimate, so I also update the estimate on my Q function. That part, I think many people that work on dynamic programming, that's standard. I'm just adding this belief component on top of it. Okay, and then I have two learning rates to play with. Alpha K is my learning rate for my opponent's play, and then beta K is my learning rate for my own Q function. Okay, so what are the characteristics of this? This is reasonable. If you look at many learning in games kind of textbooks, these are best response type dynamics. You can just think about agents acting in their best interest given the information they have. And then it's independent. Nobody needs to coordinate alpha Ks, beta Ks, anything here. The big issue here is because everybody is independently estimating their QKI. Remember what I said in learning in games for static games. Zero sum, potential. There's a lot of structure on the RIs, stage payoffs. So whatever structure you put here, the problem is whenever you have an independent dynamics, because these QKs are independently estimated, that structure is no longer the case. For instance, if we're in a zero-sum setting, which I will be in most of the talk, R1 plus R2 could be equal to 0 for each state. Q1 plus Q2 will not be. So that's the challenge, and that's why I wasn't able to make much progress in earlier days of my career on this problem, although it bothered me forever. So that's the challenge here. So what do? We will use this 2-time scale framework. It looks very simple exposed. You might have said, why didn't you do this before kind of thing. Basically, we will say that Q functions are updated at a slower time scale than beliefs. So I will basically update the belief on my opponent faster than how I estimate my own Q function. And if you talk to economists, at least you have some justification for it. It comes from evolutionary game theory, which postulates players' choices are more dynamic than changes in their preferences. So you can think about Q functions as slowly evolving player preferences. And we will see that this assumption will be key in being able to, prove convergence formally. Okay, so let me tell you a few things about our assumptions before I give you the key ideas of the proof. This is classical. Each state is visited infinitely often. Some form of, ergodicity, that's the word I was looking for, thank you. And I can actually enable it through various irreducibility assumptions. You can think about various forms of relaxations there. The first learning rate assumption is also very classical in both optimization and stochastic approximation. We say, it's decaying learning rates, infinite travel conditions. This one is the one that's new and very simple. Basically, I assume that beta k over alpha k, and there's a typo here, which should be k, goes to 0, meaning that this is the 2-time scale learning assumption. Beta k goes to 0 faster than alpha k. And let's remember what beta k was. This guy here is slower, right? It's sort of smaller than the alpha k itself. Okay, under these assumptions, basically what we can show is that pi's converge to Nash equilibrium strategies in zero-sum games, and q's go to the q value, equilibrium q values as k goes to infinity. Okay, so I'll just maybe spend a few minutes on how and why how we can prove this. Basically, what do I do? So I wrote down the evolution of the estimates again. There's a pi evolution with alpha k and a q evolution with beta k. The issue compared to static games is, these are all coupled because VK is basically, all of these different stage games are coupled because of the VKI. So I will use this beta k or alpha k going to 0 assumption to weaken this coupling between different stages. As I said, QIs are local, updated by local beliefs. So induced stage games, even though original game, Markov game is zero-sum, induced stage games are not necessarily zero-sum. Okay, so what I do is the following. I write this a little bit, discrete time update as pi k. This is writing the same thing a little bit differently. Pi k plus 1 minus pi k is just this argmax. And then qk plus 1 minus qk is alpha k times epsilon k, some error term. But this error term is basically proportional to beta over alpha. Right? I pulled the alpha here. There was a beta here already. So this guy is beta over alpha. And remember, I assume that's going to 0. So the continuous time approximation of that is, I'm just going to show you the continuous time analysis to show you basically. It's a little easier. Otherwise, everything can be done in discrete time as well. But just to see why this assumption allows us to make progress. Pi dot is this argmax here. And then q dot is 0. Essentially, making this more similar to a game with stationary payoff functions. Okay, so then I will use some standard tools from benign differential inclusion approximation theory, which allows me to characterize the discrete time updates using a Lyapunov function I find for the continuous time approximation. Lyapunov function here is just the usual. It sort of goes down and then, along the trajectory. I think what I want to share with you, this is interesting piece, is what does a Lyapunov function look like for these kinds of zero-sum games in multi-agent settings. So this is something we pulled from a very nice paper by Harris in '98. And here is the Lyapunov function for zero-sum games. He does it for static games. This is his design was for static zero-sum, repeated play of static zero-sum games. I'm going to extend that to stochastic games. And the idea is the Lyapunov function looks like you look at your, in his case, stage payoffs, in our case, these estimated QIs. And for each pi minus I, I'm taking the best response for each player. I'm summing over those best response values over all players. Okay? And why is this a Lyapunov function? I just want to go over it quickly with you to show, I think the reason I'm showing this is to show you how in stochastic games I change this Lyapunov function to make things work. So in order for this to be a Lyapunov function, I need to show that V dot is negative. So let's take the d over dt of this max. And that's basically, you can use some Danskin's theorem to show that that is nothing but for AI, you put the maximum value, which is A star. And then this is the time-dependent term, so you do pi dot here. And then pi dot is the best response dynamics. Pi dot is A star minus I minus pi minus I. This is just the best response dynamics that I was defined a few slides ago. Let me not go back. And if you plug that back in, you see that V dot is nothing but A star from here, this guy, minus A star and pi minus I. So this minus thing is nothing but the Lyapunov function itself, plus you get this Q of, S of A, essentially. Okay, so good. This is very simple. The point I'm trying to make it is if you had zero-sum structure, as Harris did in static games, this Q1 plus Q2 is equal to 0. And therefore, this term goes away. And this is indeed the Lyapunov function for his analysis. The problem in stochastic games is this is not zero. And what we did is, I think, very simple. We basically said, okay, let's come up with a new Lyapunov function. Let's just, subtract, the maximum positive thing here from our Lyapunov function so that we ensure that this negativity holds at each stage. So that was the key idea we used in constructing the new Lyapunov function. Okay, that's nice. If I combine new Lyapunov function and this benign result that I showed you before, you can show that indeed this goes to zero. Of course, that's not enough to show that I get convergence in my beliefs as well, or in the strategies as well. I think I don't want to go into the details of that, but what you do is essentially you show that asymptotically you get this zero-sum property. This part goes to zero asymptotically, which is what sort of enables you to recover the zero-sum structure of the game. Once you do that, then you show that the dynamics track Shapley's minimax value iteration, which I defined in the beginning as a synchronous algorithm over all possible states, and then you use the gamma contracting property to show that these things all converge together. So that's sort of putting things together to allow us to get convergence at the end for the stochastic game settings. Perfect. So coming back to your question. So far, I assumed I saw the agent's strategies. Oh, no, sorry. I'm going to do slowly. So first, I'm going to assume, I was assuming I know the transition probabilities, right, when I was updating my Q function. Suppose I don't know the transition probabilities of their own stage function. They just observe realized stage payoff. What do? Then I basically replace the Q learning step that I have, the Q function update using Q learning from Watkins and Dion. Of course, when you don't know the transition probabilities, this was the expectation you were trying to compute. You can basically use an estimate of that by saying, okay, instead of that, I can just follow the transitions of a Markov environment and making the sample value at the successor state an unbiased estimate of this sum. So if you just replace this in the dynamics that I showed without knowing the model of the environment, of course, now you have additional stochastic approximation errors, but you can play with the learning rates to be able to show convergence there. So this is the first relaxation. Second one is this minimal information case, also referred to as payoff-based or radically uncoupled. Suppose you do not observe the opponent's actions. So this is a killer, right? Because the whole point of the dynamics I told you was estimate using empirical frequency of your opponent. If you do not observe the opponent's payoff, opponent's action, how do you do that? I think this is a very cool idea. The idea is the following. We estimate the opponent's local payoff function. So think about this Q function, okay? So this is a function of AI and A minus I, actions itself. Think about marginalizing that with respect to your opponent's payoff. So this is my local Q function, which only depends on AI. The thing is, if I form an estimate on this, like this is what I observe my own payoff, my own realized payoff. Even if I don't observe the opponent's strategy, that realized payoff contains information about the A minus I, because this is the local Q function, and it's basically essentially a global Q function times the opponent's mixed strategy. So basically, I try to estimate the opponent's mixed strategy by estimating this local Q function, samples of which I observe because I know my own realized payoff. Is the idea clear? So I thought that's a very cool idea. So we basically use this to replace the belief estimate, and then we still use, another update to form beliefs on the value function. I use a similar 2-time scale learning framework, and then some assumptions on the learning rate. I can still show convergence asymptotically to the equilibrium of the two-player zero-sum stochastic game. So that hopefully answers your question now in terms of what we have been able to relax in informational requirements. This is a very, I think, useful setting, because really it's very minimal information. You just observe, your own action and your own realized payoff. You don't need to know even your own payoff matrix. Perfect. So this was good. I think this was a paper we did a couple years ago. Results are again all asymptotic. The next question we were interested in is, can we do something non-asymptotically here? And that's a very strange thing again, if you look at game theory literature. There is very limited results on rate analysis for best response type learning in games. In the Robinson's paper, you could extract a, horrendous convergence rate from her proof, which is k to the m plus n minus 2, where m and n are sizes of the action sets. Think about these action sets being large, 10, 100. Carlin has a conjecture, this is static games, of 1 over square root k of best response dynamics in zero-sum games. There are proofs and disproofs for special cases. By special cases, I mean tie-breaking rules or other kinds of assumptions on the payoff matrix. The only paper I knew about until a couple years ago was Harris, which has a rate of convergence for the continuous time fictitious play. And recently there's some results which are around this policy gradient, optimistic gradient type methods, but not best response type methods for learning in games. So this is what I'm going to do now. Basically, I will show you a slight variation of the dynamics that I introduced, which we call doubly smoothed best response with value iteration. It will be payoff-based, it will be independent, and basically we will show a sample complexity of 1 over epsilon to the Nash distribution, not the Nash equilibrium, and some epsilon to the 8 to a Nash equilibrium for static games as well as for stochastic games. So that's sort of, okay, so I will just maybe quickly outline the ideas. I'm running out of time. So it's going to be very similar to what I did before. I will, do the two-time scale separation a little bit differently. For convenience in the analysis, I will do an inner loop and outer loop. So it's going to be basically t times steps in the inner loop, and then there's going to be an outer loop as well. In the inner loop, so I will smoothen the best response, beyond what I did before. Namely, what that means is there's a lot of ideas here, but maybe let me parse it one by one. In order to come up with a finite sample analysis, the biggest difficulty in best response kind of dynamics is best response is multi-valued. So that's why I went to differential inclusions in the previous analysis. So a quick fix to that that's used by many people is a learning dynamics which is regularized. You basically entropy regularize your best response. That makes it some strong convex nice properties, some smoothness properties that enables you to work with single valued best response functions. That's not enough. I'm going to use this smoothing also. I will just do I will basically slowly change my estimates using a learning rate. Now, that should be enough, one would think, to get convergence rate analysis, and you can get convergence rates out of it. The problem is it's exponential. It's a terrible rate, and that's because you can, for those who play with these kinds of things, you can see that that's because, some states, this strict convexity gives you exploration of all states, but it's sort of proportional to this tau, and the exploration probability goes exponentially down with just this kind of change. So not very desirable, but one quick fix that one can use is add some epsilon, uniform exploration at each stage. We're working on it, trying to get rid of this, and I think it works without that also. But the results I'm showing you uses that aspect. So there's a lot of smoothing. That's my point in the best responses, and then you do some, again, local Q function estimate using something like TD learning. Okay, I'm going into too many details, and an outer loop does this value function estimate in a, in a slower time scale, just like what I did before, yeah, so, you combine all of these things, and then one can get both convergence as well as this epsilon to the 8 estimate. Should I say something about the proof? I mean, this was another cool idea we used in here. There are 3 different estimates. They're very coupled. We construct Lyapunov functions for each. For the best, for the beliefs, we use the Harris Lyapunov function I told you about. We use some L2 Lyapunov functions for the other one, L infinity Lyapunov functions for the other one. We want to get a rate estimate. So we basically deal with this time-varying sampling policies because of the smooth best response using, this is a time-inhomogeneous Markov noise. So basically, we need to establish some form of uniform ergodicity, which we do by using some adaptive conditioning argument. We just look at windows, large windows. If everything is uniformly ergodic, that noise converges quickly. So you combine all of these to get something in terms of convergence rate. Okay, this was high level. People who work on rate kind of stuff understood. The others just hopefully got it like it's combination of several ideas in stochastic approximation literature. Okay, so perfect. I think there's a lot of ideas now we have, and I'm hopeful we're going to be able to make more progress in this area moving forward. But everything is zero sum. That's sort of I think what these ideas do is they help me reduce things to static games analysis. Like all these errors coming from dynamics, we went back to statics. So the question is, beyond zero sum, what can we do? So we have some recent work that looks at, this potential benchmark, potential games. And surprisingly, I thought that would be easier. It wasn't. And mainly because of this reason. When you estimate payoffs at the individual level, potential structure that you have on the R's completely get lost. And then zero sum at least have some contraction property. These other things don't even have that. So, we were able to show convergence first with single controller Markov games. We have some new results that expands it a little bit more. But what I want to tell you is quickly networked Markov games, which I'm very excited about because it goes beyond 2 players. So what it is basically a simple idea. The idea isn't ours. It sort of comes from static games, which are called polymatrix games. And those are, it was defined by some other people, but Kostis had a very nice paper with Ozan, and I think Christos was there as well. They basically looked at polymatrix games, static, and showed that those games really have nice structure because correlated equilibrium collapses on Nash equilibrium. There's some LP characterization, so nice structure in the static case. So the question is, in this Markov case, how can we leverage that kind of structure? And here is our definition. There's, I think, multiple ways one can define. Well, first let me tell you, polymatrix games for n players is nothing but something like this. Payoff for E. So there's a graph between players, okay? And the link between 2 essentially means there's a pairwise payoff relation between the players. And each one's payoff, let's say R2, is the sum of R12 and R25. And R1 is R12, R13, R15. So that's sort of the networked version of going to multiple players. So this is for static games, and it's natural to define it in terms of a decomposition on the underlying payoffs, in terms of pairwise payoffs. How would you do it in the stochastic game setting where you have stage payoffs as well as an underlying Markov transitions of this state space? So that was, I think we're in the beginning of this work, but what I got excited was how to define this properly, because there are multiple ways one can define this decomposition. So the way we did it, and maybe this is not the best way, but basically we said, define the decomposition over the Q functions. Okay, so think about Qi for any V to be a decomposition over these pairwise relations between players. And what is QIV? Well, that's something we define for any V to be exactly the Q function. Why do I define it for any V and I impose this decomposability for any V, sorry, notation. So, think about the dynamics I was talking about, Q values type dynamics, the V function keeps changing along the iterations of the dynamics. So I want this decomposability to remain no matter what V I pick along the dynamics itself. So this is the way I define it, but here is what is interesting, I think. The question is, when you're given a stage payoff structure and an underlying transition probability structure, when is a Markov game decomposable or polymatrix or networked, whatever you want to call it, in the way I define decomposability. And here is our results, basically says that a Markov game is separable if and only if Ri is decomposable with respect to some graph EQ. And moreover, the transition dynamics is decomposable over the center nodes. And NC is basically nodes that are connected to everybody in that EQ. Okay? So then I have a figure writing. So for instance, if EQ is something like this, so I have the E, which is black, and I have 1 and 5, which are connected to everyone. So I can actually define the R to decompose over ER, and the transition probabilities to be controlled by two controllers, 1 and 5, and that will be a decomposable Markov game. Okay, that's the idea. So why is this interesting? Basically, it says that decomposable dynamics will happen whenever you have an ensemble of transition dynamics controlled by single controllers, meaning, you can actually simulate this by saying, for each state, I will sample one of the controllers by using this multinomial WJs, and then for that state, I will use the transition probability of that controller. And what this extends is basically the single controller Markov games or turn-based Markov games. And if you look at Tamer's book, these things actually play a big role in there. So I think this sort of why these kinds of dynamic games, single controller or turn-based, seems to be tractable, I think has some maybe connections to being able to decompose these structures in this polymatrix way that I define. Okay, so that's sort of, I think this is the result I'm excited about. In terms of what else we proved, for zero-sum versions of these network games, we can show that fictitious play converges only for star network. We haven't been able to show more general convergence for general graphs, open question. There are a lot of smart students here, so I'm happy to talk to you about that. There are ideas, but we haven't been able to prove it yet. We've proven hardness results for computing stationary Nash equilibrium for this class of games, but if you go to non-stationary Nash equilibrium, we could come up with polynomial complexity algorithms for computing non-stationary Nash equilibria for non-star networks. But that's where we are in terms of progress in this area. Okay. I think I'm right on time. So I think the goal here is to be able to show this learning dynamics for stochastic games. We were able to do it using this 2-time scale learning framework. We were able to have some finite sample results. I'm very interested in getting more general results for potential stochastic games, non-asymptotic analysis for network Markov games, and then go from there. We have a new paper on function approximation embedded. Then you have massive action spaces as well as state spaces. How can you actually combine these ideas with function approximation? Well, because this was a tabular case. Yeah, with that, maybe I'll conclude and see if there are other questions.
Great talk, impressive. One question, you observe the state is a common state space, right? That somehow combines the states of all of the agents.
Yes.
What if you can observe your own state, but you don't observe the states of the other agents, so you are in sort of some form of partial.
Yeah, it's very hard. I think Kai Ching has some results on that, partial observability. I don't know which of these results would generalize in that setting. We haven't looked at that.
And another, if you allow me one more question.
Of course.
So what if the actions are, you use some deep neural, whatever, some neural network for the policy, in terms of the distribution of the actions of every player. Is that the problem, or?
So here we do not use any convexity or anything like that. This is just this action space, large action space.
So it could be any mapping.
It could be any mapping, so it doesn't matter.
Yeah.
So that's why there's no,
yeah.
It's not gradient based.
No.
It's best response, and we use sort of different kinds of properties.
Great,
so
thank
that
you.
Would work, yeah.
Questions? I have a quick question. So you mentioned going beyond the zero sum. Can you elaborate a little bit on the significance of that in terms of the applications you were talking about earlier in reinforcement learning and application of that? Like, what do we achieve by going beyond the zero sum scenario?
Zero sum is a benchmark. I view
Yes.
it as a benchmark. In many of the settings that are of interest, it's not zero sum, right? There's potential structure in the traffic game that I mentioned, or variations, more relaxations. The networked game structure happens a lot. This is why I'm excited about that aspect. So my hope is to go to this networked case, and then, it's still for zero sum. But beyond that, I think there's more one can do. If you can actually decompose it across this multiplayer settings, I think there's a lot of hope there.
More questions?
I guess at a general question, my understanding of the results is that you're looking at a setting where it's possible to kind of exhaustively explore the state space. There's a finite set, and you're looking at timescales where the players visit all the states many times and can kind of observe enough to kind of learn some model of the game. I would imagine there are lots of settings where that's simply not feasible.
Absolutely.
And obviously you need some additional assumptions.
Yep,
Are
yep.
there ones that are what are the kind of natural ways of restricting the game in such a way that you could talk about players who could learn good strategies, but or converge to good strategies, as you're saying, in a relatively
That's
on a shorter time scale.
Good question. This is our mathematicians' tricks to be. If you have any general game that can support any Nash equilibrium over that state space, you need to have some assumptions that says you need to be able to explore if you want the general result of the forms I'm talking about. In some cases, you don't have that. This is an online case where I'm allowed to explore. There's offline cases where you have data sets where you can't do that, in which case you can still analyze, but you can say something like, okay, I converge to whatever data coverage your data set allows, and best in class. So you can have guarantees in terms of whatever you can explore. If the underlying Nash equilibrium explores everything, you can't, of course, converge to that, but you can converge to something at a lower support. So that kind of guarantees you could obtain. Does that make sense? And there's a lot of work in the offline RL setting in particular that assumes results on data coverage. And without that, what you're allowed to converge.
So I was going to ask you, for non-zero sum games,
Yes.
the strategy that's often used in learning is counterfactual regret, which is a little more convergent. But you're obviously focusing on the zero sum game where fictitious play is a nicely strong strategy.
Yes.
Curious if that's on your list of things to look at some point, or?
Yeah, I haven't looked a lot on online learning where regret-based strategies are more. This is best response type. I guess this is my econ. That when you talk to an economist, best response is sort of the type of thing they find more natural for autonomous agents. Regret type dynamics. The thing is, you could look at regret type dynamics. There's a lot of structure shared in terms of the type of results you can get for zero sum, or like when things converge to for non-zero sum. correlated equilibria, right? That's the same case in regret-based dynamics as well as this type of dynamics. So I think the underlying mathematical structure has similarities to say in the class of games I study with this dynamics, maybe I can look at regret-based versions. I haven't done that, but it's of, I think, that kind of synergy in between.
Further questions?
Super.
Thank you so much.
Thank you. Thank you.